this computer. Good. Hi, everyone. So today we're very happy to have Horacio Casini giving us a talk from Argentina, all the way from the summer. And yes, he's going to be talking about entropic order parameters for the phases of quantum field theory. Thanks so much, Horacio. Please.
Okay, thank you, Nima, and thank you all of you for having me. Well, this is it's based on two works with Marina Huerta, Javier Magán, and Diego Pontelo. These are the numbers, one from the last year and one from the 19. And it's about some entropic measures that are used for order parameters for phases of symmetries in quantum field theory. So this is a brief plan of the talk. I will start explaining a little bit the idea of describing quantum field theories by operator algebras attached to regions. And in this description, I will describe two simple properties, additivity and duality of these algebras, and how the breaking of these two properties is related to the notion of symmetries, to generalized symmetries, in fact. And the type of symmetry depends on the topology of the region where these properties are broken in the algebras. In this situation, when you have some of these generalized symmetries, you have multiple possible assignations of algebras to a given region. And these multiple possibilities allows you to define the entropic order parameters using the relative entropy. And this entropic order parameter satisfies a nice relation, a kind of, we call it certainty relation, because of reasons I will tell later. And this relation relates the statistics of dual entropic order parameters. Entropic order parameters assigned to complementary regions of space. At the end, I will describe the behavior of these order parameters and try to relate them with the usual order parameters, for example, the Toff loop, the Wilson loop in gauge theories, and give some heuristics based on this certainty relation on how these parameters behave and what is the reason, for example, for an area law and constant law, etc. So let me start. This is a preliminary transparency. So this is about formulation of quantum field theory. The usual formulation, the oldest one, is in terms of quantum fields. So they are distributions, operator value distributions at the point. And it is known also from very old time, the 1950s, that instead of describing the theory in terms of quantum fields, you can describe it in terms of its expectation value, or expectation value of products of these fields in vacuum, the correlation functions. And these two descriptions are equivalent. And here is somehow you have a simpler somehow description in the sense that you are talking about numbers. There is also another formulation that is very old, is from the 1964, this Hack-Kastler formulation, that is based, instead of fields at the point, is based on operator algebras attached to a region. So you take a region of a space-time, and then you produce all the operators that you can produce inside, for example, mirroring and multiplying and taking linear combinations of your fields. And then this gives you an algebra of operators, and then each region has its attached algebra. And somehow it's kind of a basis independent formulation of the theory, because you can have, for example, different field generators of the algebras that give you the same algebra. For example, a free field or a free field to the power of cube, for example, will be giving you the same algebra. And there is also dualities that you can describe the theory in terms of different set of fields that give you the same algebra and the same theory. So, but then you can ask, what is the same step as in here? How can you get from an algebra of operators, how can you get a number out of the vacuum, for example? And if you think a little bit about that, the only thing that you can produce out of the state and an algebra are kind of entropic properties or statistical properties of the algebra, for example, entanglement entropy, mutual information, range entropies, etc. And this allows you to give numbers to the algebras. So somehow this is the type of things I will be talking about. Of course, we do not know up to now if there is a kind of equivalence in this sense. If you have all the, let's say, the mutual information, you can regain the theory, the quantum theory, as in here. But it would be nice if that would be the case. But certainly, many people, I think, I believe this is correct. But up to now, we don't have a theorem. Well, let me put a little more.
Sorry, Horacio.
Yeah, sure.
Can you say, I guess I didn't quite understand. So what is it that you're saying, conjecturing whether it's correct or not? I did not quite.
No, I would say the following. If you have, for example, all the set of all the mutual informations of, let's say, pair of regions, you can reconstruct. Of course, we do not know the set of axioms that this has to satisfy. We know that it has to be monotonous, positive, etc. But I do not know if we have already like a full set of axioms. But if you think you have a set of mutual information, maybe you can reconstruct the quantum theory. That's some similar case as in here. From all the expectation value, all the correlators, you can reconstruct the quantum field theory.
I see. Thank you.
Yeah. Okay.
Also a trivial question, you draw some arrows, but do you have arrows between the other, for example, this formulation and the Wyman functions or things like that?
Well, we have some relations between, for example, mutual information and the Wyman functions at large distances. You can see that the mutual information goes like the correlator of lowest dimensional operators in conformal field theories, etc. But in general, for general regions, the direct relation between these two is supposed to be very complicated and is not known. But you can take, for example, you can extract for a conformal field theory, you can extract from mutual information, you can extract the set of operator dimensions, just taking the long distance limit and looking at how this mutual information goes in a series of powers.
Thank you. Yeah.
So let us start with algebras. If you take a set of operators in Hilbert space, you take the commutant. The commutant, that I will call it A prime, is just the set of operators in Hilbert space that commute with all operators in A. And there is a very nice theorem by Newman that tells you that for this, let us think you have a finite dimensional algebra for simplicity, and then you can ask when this set of operators is an algebra. Of course, it has to be closed under linear combination and products, but another way to say that is that it is equal to the double commutant. So all double commutants of some set of operators are algebras. And then for regions in space-time, in Cauchy space-time, we have a kind of operation that is also kind of complement, that is a causal complement. If you have, for example, this region V here, you take all the space-time points that are spatially separated, this part and this part. And this is a causal complement, the set of points that are causally disjoint, let's say, from the region V. And if you take the double causal complement, you get this diamond here. And it's natural to think that operator algebras are really attached to these causally complete sets or diamonds, because, for example, if you have an operator O here, you can write it using the equation of motion as an operator in this smaller region V. So the algebra of the diamond region is in fact equal to the algebra of the region B. So really, you can make things simpler by just taking these causally complete regions. So we think that then that you have a von Neumann algebra attached to each causally complete region, and you already have this nice thing that you have this von Neumann theorem and these causal completion regions, are equal to the double complement. And there are further structures that looks like the same for regions and algebras. For example, if you take the intersection of two regions or intersection of two algebras, it gives again a causal region and an algebra. And if you take the union and then do the double causal complement, this is again a causal region. That is the smallest one that contains R1 and R2 in this case. And the same for algebras. If you take just the set theory union of the two algebras and then complete with a double commutant, you get the smallest algebra that contains the two. With these two operations and the causal complement, the structures of space-time regions and algebras form what is called orthomodular lattices in the set theory sense. And now we want to understand what is the particular relation between these structures for causal regions and for algebras in a quantum field theory. So the minimal requirements for a quantum field theory are these two. If you have a region R2 that is bigger than R1, R1 is included in R2, then the algebras have to have the same inclusion. The algebra of the bigger region has to contain the algebra of the smaller region, because it is somehow telling us what is the meaning of locality of this operator, in the sense that if an operator belongs to a small region, then it also belongs to a region bigger than this one. So you have a sort of ordering relation, and then we have also causality that tells you that, for example, this operator O here inside this diamond is contained in the commutant of all operators that are outside in the causal complement because of the microcausality relation. So it turns out that then the algebra of this region here, for example, this diamond, has to be included in the algebra of the complementary region R prime commutant. The commutant of the algebra of the complementary region. That just, it tells you that operators based on spatially separated regions just commute to each other. But then one can ask, how can we enlarge these relations at the maximal possible level, let's say? So what would be the maximal harmony between algebras and regions in this sense? And you can say, well, and that we have called this complete theory. Complete theory will be some theory that satisfies this maximal harmony between algebras and regions. And this is given by this relation that just tell that the assignations of algebras and to regions form an homomorphism of lattices in this set theory sense. For example, the first one is called Haack duality, is that the algebra of a region is equal to the commutant of the algebra of the complementary region. So this is an enhancement of this causality relation. The second one is additivity, and is quite natural from the point of view of quantum field theory. It tells you that the algebra of a bigger region is just formed locally by products and linear combinations of the algebras of smaller regions. It's somehow what you get from thinking that the algebras are generated by field operators smeared in some smaller regions. And this other property, this intersection property, is analogous to this one, is kind of dual to this one, But in fact, I will not talk much about this intersection property because it just follows from these two. If you think that these two always hold, you can prove that this one. And the same if you think Hug duality and intersection property always hold, then you can prove additivity. So I will always keep talking about the first two, Hug duality and additivity. So this would be the case for a complete theory. This is the case, for example, for a free scalar field. Now we want to understand what happens if you violate some of these properties. Let me say that I will mainly talk I will talk mainly of regions that are based on pieces of a, so I will talk about regions that are based on the same Cauchy slice, let's say, like T equals 0 slice. So I will forget in the talk the fact that the space-time is 4-dimensional, say, or D-dimensional. I will always think my regions are based on a spatial slice. So of course, for each spatial slice, I have the causal diamond and this one-to-one relation.
Sorry, Horacio?
Yes.
If I take additivity for complementary regions, doesn't that give me Hug duality?
Additivity for complementary regions. So you say, okay, you are taking the full space here.
Yes. The fact that the algebra of A and A prime should generate the whole algebra of quantum field theory, shouldn't that give you Hug duality?
I don't see, let me see, if I take.
So maybe another way of saying that, so take Ringler wedges. But
Yeah.
what we're saying is that A, the algebra of A and the algebra of A prime is generate everything, right? So
Yeah.
there's nothing that is, yeah, I guess that's sort of, so there won't be an you won't be able to generate a charge in the left side and annihilate it on the right side.
Well, sorry, but how do you know that they commute from a region and the complement? How do you know they commute?
That's locality axiom, right?
But
so,
that's not, there is no axiom like that in this list.
Well, let me see if you.
That's the complement, he said, no?
Uh,
I mean, that's saying that the complement is that is like they commute, but if you don't impose that, I'm not sure.
Oh, it confuses me very fastly what you say, but
we don't
I have to think about that.
Yeah, it's not an important comment. It's not an important comment at all. I mean, yeah, never mind. Maybe we could discuss this later. This is not an important thing.
Okay. Oh, then, well, then let me see what we can do to like weaken these properties. We are going to weaken these properties in the softer way possible. So we will assume that topologically trivial regions such as a ball satisfies additivity in the sense that the algebra is generated by algebras attached to smaller balls whose union is the big ball or the big region, which is topologically trivial. So this is a natural assumption. Is there are some counterexamples with generalized fields to that. If you know the use of generalized fields in holography, you can see that. But this is just to restrict ourselves to some particular problems that are attached to the topology of the region. So algebra region problems might arise for topologically non-trivial regions. And then if you have this idea that additivity holds for topological trivial region, we can always produce a net. A net is just an assignation of algebras to regions that satisfy causality. a net that we will call it the additive net. It's just you take some region R that can have a topologically can be topologically non-trivial, and you produce an algebra for it, just doing the union, the algebraic union of the algebras of all balls contained in it. And this is the additive net, and it's somehow the minimal possible one, because if you have a region R, it already contains all these algebras of these balls because they are included in R, so it has to contain this algebra, and the assignation of the additive net is the minimal one. And then you can think, what is the maximal possible assignation of operators? Well, it has to be the one that is just related to the commutant, is the commutant of the minimal assignation for the complementary region, because it's the maximal assignation, this one, that satisfies causality. So you take the additive algebra for the complementary region R prime, and then you take the commutant. And then the question is whether these two are equal or not. If they are not equal, then it must be the case that the maximal algebra for the region R is just the additive algebra of R. It contains the additive algebra of R plus some other elements, some other operators. That because of this, these A operators cannot be formed additively inside the region R, right? So they are kind of non-local inside the region R. This is why we often call these non-local operators, but one has to be aware that they are maybe locally generated in other bigger balls, right? Well, and the same happens for the complementary region R prime. The maximal algebra to R prime would be the additive algebra for R prime plus some other non-local operators. And this set of operators A, B are, we call it dual non-local operators. And they do not commute to each other. One can see that they cannot commute to each other, and they are non-locally generated, each one in its proper region. Once we have this situation, one cannot take a net that is additive, because this net, the additive net would be this one, and that satisfies duality. So the additive net does not satisfy duality. You have here the additive net, the commutant is just the maximal algebra and is not the additive algebra. It has something more. So once you have this situation, you either lose additivity because you are taking some other algebra that is bigger, or you lose duality because you take something smaller, for example, the additive net. So and it's not possible to repair that situation. It's important that these non-local operators are non-additively generated inside the topological non-trivial region, so you cannot generate it by products of small operators, but they can be formed by multiplying small operators in a bigger region, for example, in a ball containing these operators. I will show some examples below. Another thing is that these non-local operators always appear in dual sets, like these A's and B's, and they do not commute to each other, as I said. And as these things here are algebras, so it must be the case that these non-local operators have an inner multiplication between themselves. So if I take two of these A's, multiply of them, and then they will belong to some class of other A's, and then you have some fusion rules for the A's and fusion rules for the B's. In particular, in the examples I will show, these fusion rules are always related to groups. But more general cases are also possible in some situations.
So Horacio, just one little thing, something that I've always been confused about. So up to here, it seemed like the whole analysis was very general, right? There was no need to introduce symmetries or anything. And these fusion rules are the first place, at least in my naive mind, that symmetries sneak in. So these could be proved as like there's some sort of an OPE for fusion rules for these non-local operators. How do you approach this problem at all? Like, how would you show such fusion rules? Like,
No, well, okay. Let me say, if you instead of taking, I have put here operators, right? But if you take classes of operators, classes in the sense I take one representative here and the full additive algebra multiplying it, this is form a class of operators. These classes of operators are bounded to have fusion rules. This is obligatory because it's an algebra and then it closes in the product. So you can think you can think these classes of operators form a fusion algebra, let's say. And in some situations, we have shown that in the examples I will show, you can in fact choose operators that close the same algebra, close an algebra, fusion algebra. But here there is nothing like certain. When you talk about operator product expansions, it looks like you have taken some limit, or here is nothing. There is no limit, so it's just big operators. Let's say it's mere operators.
So this is at the level that I could just take two regions of quantum field theory and say, because let's say I have additivity. If I pick A and A prime from region 1 and region 2, therefore there will be, their multiplication could be expanded in terms of operators in the 1-2 region. So these ends are really just in principle.
Yeah, all these belong to the same region, right? All these belong
in this
to
example,
the same...
yes.
Yeah.
Okay,
yeah, because you in principle you can decompose. This product belongs to the algebra, to this algebra, and then you can decompose it in the same structure, right?
I think that the part that's so magical is that once it becomes a symmetry, then these A and A prime, these N coefficients become representation theory factors.
Yeah, well, in general, it would be, in general, you only have this fusion rule, and you don't know what possibilities there are. But working harder, in some situations, you can say there are smaller possibilities. For example, the fusion comes from a group. I will show something about that.
Thanks so much.
So this is the first example. The first example is just a case of global symmetries that corresponds to regions where additivity and duality fails, that have homotopy, non-trivial homotopy group pi 0 or pi d-2, where this pi 0 is just means it is non-trivial, means that your region has more than one connected component. For example, these two balls here. I will just stick to these two balls, R1 and R2. This will be my region where topological, where non-local operators appear. Another thing is that when I'm saying that I take a quantum field theory with a global symmetry, in fact, I'm cheating a little bit, because what I'm taking is just the orbifold. It's just, I take the full theory F, and then I project to only to operators that are invariant under the global symmetry. Once you have a quantum field theory with a global symmetry, you can always go to this orbifold theory. And you can also go back from the orbifold theory to the full theory. This is the DHR analysis, Doplicher, Haag, and Royce. So we will only consider operators that are invariant and the full global group. In that case, you can see that you can take, for example, a charge operator here and anti-charge operator in the other ball. And this operator belongs to the neutral operators. If you combine them adequately, it's a neutral operator in the full algebra, but it cannot be formed additively because this operator here does not belong to the orbifold, right? neither that is. So you need the two balls, and you have the operator there, but you cannot form it by products of operators in each of the balls. This type of operators, we call it, people somehow call it intertwiners, depending on what on your inclinations. Well, you have an intertwiner in the two balls for each representation of the group of symmetry. That would be the non-local operator for the two balls. For the complementary region, that is the outside part of the two balls, there is another non-local operator that is called the twist, that is labeled by conjugacy classes of the theory and is forming the following way. If you have a global symmetry, there is a theorem that tells you that you can always produce an operator that implements the global symmetry just in a region. For example, inside this dashed line. Inside this dashed line, this operator tau c just produces one group operation inside, but nothing outside. So, and this is the twist. And the twist in a non-abelian case is not invariant, so it doesn't belong to the orbifold, but you can sum in the conjugacy classes of the group, and then you get an invariant operator. So the twists form the non-local operator in the outside part. And you can see that the product of twists have the fusion rules of conjugacy classes of the group, and the products of intertwiners have the conjugacy, the fusion rules of representation of the group. How does additivity and duality works in this situation? Well, you have, for example, if you have the additive algebra of the two balls, so I don't take the intertwiner, the charge operators are not there here, I have only neutral here and neutral here, and I take this is the additive algebra, I take the commutant will contain all the additive operators outside, plus the twists, because the twists just commute with neutral operators here, so the twist will appear there, naturally. Instead, if I start from the additive algebra in the outside part, that doesn't contain the twist, then the commutant will contain the additive operators here, but it will also contain the intertwiners, because the intertwiners will commute with the additive operators outside, which does not contain the twist. The twist will not commute with intertwiner, because the twist make a group operation in this charge operator, and they do not commute to each other. So this is a natural situation where you have problems of algebras and regions for this type of topologies. Now let us think the case of regions with non-trivial homotopy groups pi 1 or pi d minus 3. For example, we have this ring-like region in 4 dimensions, and in 4 dimensions, the complementary region have the same type of topology, but in high dimension have non-trivial p d minus 3. So we think we have a kind of non-local operator that cannot be generated locally in this ring. We call it A, and for the outside part, we have some B operator. And in this situation, in 4-dimension higher, you can actually prove that this the fusion rules coming from this situation, in fact, is coming from abelian groups. There is an abelian group behind the fusion rules, and the commutation relation between the A operators and the B operators is always fixed, is given by this commutation relation where this chi, so let me say, you can think the A operators are labeled by representations of abelian group, and the B operators are labeled by elements of the groups itself, or vice versa. So the group of A's and the group of B are both abelian and are just dual abelian groups. And this is just the character. So this is a number, it's a phase, it's a character of the representation B applied to the element A. So I will not give the details of this, but it's quite simple to understand how this comes from. Because if you have a ring like this one, the dashed line, you can put inside one of these non-local operators, like this one, twisted to itself. But inside the ring, this non-local operator A is in fact local because it is contractible to a point. But then you can do local operations here and to convert this operator to a product of two line, let's say circle or loop operators. Two loop operators conjugate to each other. So they are conjugate to each other. And you see from this picture that the product of these two classes, A and A bar, just give you something that is local, is locally generated, so is equivalent to the identity, let's say the identity class. So it means that in your fusion rules, A times A bar is just the identity, and this give you immediately that the fusion algebra is just the fusion algebra of a group, of an abelian group. If the group is non-abelian, for example, A times A bar is not the identity alone, but it has some other things. Well, but let us think in gauge theories, in a specific example. So in a gauge theory, you can think, well, naturally the non-local operator will be given by some Wilson loop with some representation R, let's say. But it happens that not all Wilson loops are unbreakable. So not all Wilson loops are non-locally generated in the ring. Why is that? Well, the first reason why a Wilson loop can be broken into pieces in such a way that is additive operator is because you have a charge operator with the same representation. So you can write down the Wilson lines like this one and take products of these Wilson lines along the line of the Wilson loop. In the product of this and in the algebra of these Wilson lines, it will appear the Wilson loop. So the Wilson loop can be broken to pieces. And in the case of non-abelian gauge theories, the adjoint representation is always breakable. You can always write down this Wilson line where you have the field operator here in the adjoint representation. So the adjoint representation can be broken into pieces, and so can be broken into pieces all the representation formed by products of the adjoint representation. It turns out that what you get once you take out all the algebra generated by the adjoint representation is representations. The thing that remains can be labeled by representations of the center of the group. So you have Wilson loops, let's say unbreakable Wilson loops, or just labeled by representation of the center of the group. In general, it's a very small group, a finite group. For example, for SUN, is just set N. And for the complementary region, what you have there is the Toff loops, kind of, let's say, electric flux in a surface with boundary in B, but it's an electric flux only in the center of the group, in such a way that it's an operator that only depends on B and not in the surface that you are putting there. So at the end, what you get is just, yes?
I have a very basic question. I think I'm a little bit lost. So you started by talking about attaching algebras to causal developments of balls, right? To the double cones, right?
Yeah.
And you discussed the case of two disconnected regions. Now, in this example, this is a torus, right?
Yeah.
And so the algebra that we're associating with the torus here is it the von Neumann algebra? What is it like? How is it defined?
Yeah, it's a von Neumann algebra. Like
So
yeah, we always think it's a von Neumann algebra.
But because before you said, so for it to be a von Neumann algebra, it has to be equal to its double commutant. Right?
Yes.
So for the case of, you said that we're going to assume duality for topologically trivial regions, right? If you assume duality, then you sort of get the fact that the algebras are von Neumann.
Additivity, yeah. Yes, also.
So
yes.
Here, what are the assumptions? I mean, is this already an assumption that the algebra of this torus is a von Neumann algebra? Does it satisfy duality, for example? Is the algebra?
No, well, there is a different. All algebras that I'm talking about, I think they are von Neumann algebras, right? But it's different to say that this satisfies duality. So it will, for example, in this situation, if I take just the additive algebra of the ring, then the operator A is not there, right? It's not additively generated, so it's not there. So this is a von Neumann algebra, it closes in itself, but it doesn't have the A operator. So the complementary, so if I take the commutant of this ring, I will obtain the operators that are additively generated outside, plus this B operator. Plus this B operator.
This is the case of a global charge, or are you thinking of gauge theories?
No, I'm thinking in the gauge group. For example, let us think in Maxwell field. In Maxwell field. So you take the F mu nu inside the ring and you generate an algebra, right? So yes. Then the commutant of this is just the F mu nu outside everywhere, plus the electric flux crossing here. The electric flux and the magnetic flux, in fact, crossing here, because they will commute with F mu nu in the ring.
So I understand the situation that you're describing for gauge theories, but what I'm asking is that the story would apply to global symmetry as well, or is this a specific to gauge theories? I mean, a priori, given the algebra, how do I know I have a gauge theory or not? Right? I'm trying to.
Okay. No, the point of view is somehow. Suppose you have a theory, and then you take a ring, and then you say, well, do I have duality and additivity for the ring? If the question is yes, then you don't have this kind of generalized symmetries attached to rings.
I see. Okay. Yeah. Okay.
If your question is no, I don't have it, then it means that you have some non-local operators. They have some fusion rules, and you can check that there is an abelian group there. So you obtain the abelian group. You don't know where it comes from. You don't know the structure of the theory or whatever. It's just at this level, it's just that you have an algebra of non-local operators, right?
I see.
You cannot reconstruct the gauge group. You can reconstruct only the generalized symmetry.
Right. Thank you.
Okay. So, in conclusion, for this for this part of the talk, when additivity and duality fails, there are multiple possible nets that you can of algebras attached to regions. It's not only one. The additive net does not satisfy duality because the commutant of a region contains the non-local operator, so it does not satisfy duality. You can construct a dual net just by adding to the additive operators the non-local ones. You start, for example, adding this A operator here, but of course you cannot add the B operator outside because they do not commute, right? B does not commute with A. So in fact, what happens is that you can have several different nets satisfying duality, but of course none of them will satisfy additivity. What is happening is similar to the idea of satisfying the Dirac quantization condition for the electromagnetic field, for example, that you can choose some Wilson loops at the cost of choosing some other electric fluxes that satisfy some particular quantization condition. So somehow the nets that satisfy duality are these Haack-Dirac nets that satisfy some quantization conditions. But of course, they do not satisfy additivity. Well, the symmetries are encoded in the algebra of these non-local operators. And this, all this idea just matches perfectly well with this idea of higher form generalized symmetries by these people some years ago. And if you have a higher homotopy groups where additivity and duality fail, they will correspond to higher generalized symmetries or higher form generalized symmetries. So it's just a different starting point, a different kind of description of the same kind of ideas. But let me now pass to the idea of these entropic order parameters. So the idea is that these entropic order parameters will profit from the fact that there are more than one possible algebra for the same region. To define these entropic order parameters, we will need this idea of conditional expectation. Conditional expectation is a mapping from an algebra to a subalgebra. There is a linear map, linear positive map to the subalgebra that has some specific property that is given by this relation that just tells us that this mapping from M to the small algebra just leaves the operators in N invariant. It leaves the operators in N unchanged. But from the point of view of this talk, the importance of the conditional expectation is that it allows you to lift a state that is defined only for N. You can uplift it to a state that acts on all M. In the language that I'm using, a state is just considered as a function on an algebra. It's a function that gives expectation values for all operators, that gives numbers for operators. So if you have a state in the small algebra N, you compose this function with a conditional expectation, and this composition give you a state in the big algebra M. The conditional expectation takes from N to N, and then the state takes from N to the numbers. In the particular situations that I'm describing, these conditional expectations are produced by the non-local operators themselves. For example, let us take the two balls. In the case of global symmetry, we have two algebras, one that contains the intertwiners, that contains the charge anti-charge operators, and the other that do not contain it. And in order for going from the big algebra containing intertwiner to the one that doesn't contain it, you have to kill the intertwiner. And how you do that? Just average using the twist operator. The twist operator will only change this charge operator, and if you average over the group, it will give you 0 for the intertwiner and leave all the uncharged operators or the additive operators in themselves. Well, then the idea is that you have always the big algebra containing the non-local operators, and you can produce two states in the same algebra. One is the vacuum, and the other one is the vacuum composed with the conditional expectation. So one of the states will give you some expectation values for the non-local operators that are non-trivial, and the other state will give you 0 for the non-local operator. It just kills the non-local operators because of the conditional expectation. So, and then you are comparing these two states with the relative entropy. The relative entropy is a tool in information theory that just compares two states and evaluates the distinguishability of these two states. So if the two states are equal, it gives you 0. If they are very different, it gives you a large number. And it's nice because this relative entropy is already well defined in the continuum limit itself, so it doesn't, in principle, require cutoff. even if you want to compute it, maybe you can use cutoff as an intermediate step. So this relative entropy will measure exactly some kind of statistics of the non-local operators, because it compares a state with, let's say, with the non-local operators, and a state will just give you 0 for the non-local operators. But it compares them in a way that do not depend on the particular non-local operator that you are choosing, because it's just a property of the algebras. So it's a function of the geometry and nothing more. For example, if you have this thing here, you have these intertwiners, and you can take very small charge operator here, or very smear charge operators. They are the same in the sense that they both produce the same algebra when accompanied by all the neutral operators. And so, in fact, this entropic order parameter will give you an idea of the expectation values of the best ones of these non-local operators, the ones that have the higher expectation values. So let me put it in a more formal way. We have some region R with topologically non-trivial. We have the additive algebra plus the non-local operators. The conditional expectation eliminates the non-local operators and goes to the additive algebra. And the same for the complementary region. You have the additive algebra in R prime with the non-local operators and some conditional expectation that eliminates these B's and go to the additive algebra. And in the vertical direction, we have just the commutant. The commutant of the additive algebra plus non-local operator is just the additive algebra in the complementary region, and here the same. Once you have this structure, you have this interesting property that we call the entropic certainty relation, that gives you a constraint satisfied by the two possible order parameters, entropic order parameters, one due to this conditional expectation that measure the B operators, and one that measures the A operators. So you have these two relative entropies always add up to some number, some fixed number that depends only on the group, in this case, only on the group of symmetries, the log of the size of the group of symmetries. The group of symmetries satisfied by the A or the B operators. In general, mathematically, situations more complicated can happen where you don't have a group, and here this is called the index of the inclusion of this algebra inside this algebra, or this algebra inside this algebra. So these are some references about this. So at this moment, this relation is proved at the full rigor. So really, it holds also for type 3 von Neumann algebras in quantum field theory. But why we call it entropic certainty relation? Well, because it looks like a high information of an uncertainty relation. Let us write it again, this formula. We know that the relative entropy is always positive. So it means that this relative entropy is always between 0 and log G. And this other relative entropy is always between 0 and log G, the same. But this relation tells us that we cannot saturate both relative entropy at the same time. You see that saturation means that is the maximum value of this relative entropy. It means that this is the maximal difference between these two states. It means that the non-local operators have the maximal expectation value. And you see that these A and B operators do not commute to each other, so they cannot have the maximal expectation value at the same time. This is what this relation is telling us.
Sorry, Horacio, when you say maximal, what is it? Is it the state that you're varying, or what is the thing that you're varying?
No.
Maximal in what sense?
Well, for example, if I have this ball here, let us think what we expect in this case. We have these two balls, and my non-local operator is an intertwiner, right?
Sure.
So I can play the game of choosing different charge anti-charge operators in such a way that obtaining the maximal expectation value, right?
So
This is a difficult thing. This is a difficult thing, but you can play the game.
so
For example,
supremum is over all intertwiners.
Over all intertwiners, yeah.
I see. Okay.
So suppose you have these two balls. Suppose these two balls are very far away, right? So the intertwiners will have a very little expectation value. So it means that these two states are very similar to each other, and the relative entropy will go to 0 in this situation. When you have this situation, the other relative entropy, the one given by the twist operator, is going to be the maximal thing. Why? Because in that case, you have a lot of space here between the two balls, and you can smear the twist very softly, such a way that it looks like the full group operator acting on vacuum. So it have expectation value near 1.
That's right.
Right? In the other situation, when the two balls are near to each other, the twist is very squeezed, so you can smear very small region, and then the expectation value of the twist go to 0 and the relative entropy go to 0. While in the intertwiner, you can play the game of taking two charge operators very near to each other, such a way to have a maximum expectation value and a maximal relative entropy.
But I mean, for a fixed intertwiner as well, can you vary the state omega so that you saturate one or the other inequality? For example, if you take a conditional expectation, and if I pick state omega that is preserved under that conditional expectation, right? So I can try to force some of these relative entropies to be 0.
Yeah, well, this relation holds for all pure states, pure global states.
Yeah, I mean, sure, but I mean,
then you can play the game of changing the state. I don't know what you can get from there, but in principle, you can play the game of changing the state in such a way that, okay, you say, for example, in such a way that one of them is 0 by construction.
That's right. That's right.
So the other will be maximal. Yes, in that case. So you are in that case you are proving that the other operator here in that state there is at least, for example, one twist, one with expectation value 1 in the, so it's invariant. Yeah, that's what you're saying.
Yes. Thanks so much.
Other thing that you can use this relationship to put lower bounds and upper bounds on this relative entropy by relative entropies in smaller subalgebras, for example, a subalgebra of non-local operators without the additive operators. And these things in general are functions of expectation values that you can compute. It's easy if you have the expectation values of the B's, it's easy to compute. For example, this relative entropy is just a numerical function of the expectation values, and here the same. And with that, you can put our lower and upper bounds to this more complicated quantity and give you a handle on computations. For example, here I show you very fast because I have no more time. The case of some particular group of Wilson loop operators for the Maxwell field in a ring, where you can compute these relative entropies, and for example, for thin loops, it goes exponentially to 0 with the perimeter, so we have a kind of perimeter law. And for thick loops, it goes without upper bound logarithmically with the size, increases up to infinity, because in that case, in this present case, this log G is in fact the log of G is just a group of integers, so it doesn't have any upper bound.
But because this is log of G, because you're talking about finite index, this is finite groups, right? Like the moment I take a continuous group, then I don't have an inequality, right?
Yeah,
I don't get anything.
Yeah, it's finite groups. for example, for the case of gauge theories, you almost always are interested in finite groups because it's the center of the group is a finite group in general. So it's not the gauge group itself. If you have Maxwell field, the center is a full group that is continuous and this is divergent, right?
So that is sort of the global symmetry then, right? There's a sense in which that center
it's kind of people call it the global generalized symmetry, right?
Yeah. Okay, thank you.
So, but what I mean is that there are many situations in which you are interested in finite things here, but also you can also, for example, in here, we don't have a finite thing, but we can still use this lower and upper bound. This here, you have to work out in such a way that things cancel here and give you something finite, but you can do it. And then you can get upper and lower bounds to the quantity that you are interested in. Let me pass to the final comments that in the case of gauge theories, let us think in the case of gauge theories, you can compute the things in, for example, in the Higgs phase, and where you get that for example, there is a entropic order parameter related to the Wilson loop that has a constant law, and a entropic order parameter related to the top loop that has an exponential law in the area, and one can think the same will happen for the confinement phase, where now the Wilson loop is the one that has exponential law in the area. For the conformal phase, you would have both of these type of ring operators with loops. Relative entropy will have a perimeter law depending on the size of the loop and divided by the width of the loop. Let me say something more. For example, in the conformal case, because of this, for example, if you think you have a conformal case in four dimensions, the geometry of this loop and the geometry of the outside region are conformally related. If you take the loop, the torus right, it depends only on a cross ratio, on a specific number. And this cross ratio is, for the outside part, is just 1 minus the cross ratio for the ring itself. And so using the entropic certainty relation, you can actually predict the value of this, of some particular relative entropies for a cross ratio 1/2, and it gives you just the logarithm of the center of the group in the conformal case. You have other relations you can predict that I will not enter into details. But this for us was very like, it's still puzzling for us. For example, you have these super Yang-Mills theories in 4 dimensions that have a free parameter, and you can move the free parameter and it's always giving you the same thing. Even if the expectation values of operators will depend much on that. So we do not know, for example, if you change the value of the coupling constant, it will change, for example, the expectation value of the Wilson loop and the top loop in the different ways, such a way that is always satisfied, or just is a trivial kinematics. We do not know up to now what's happening here. So let me finish with this heuristic idea on how this, because you have these pairs of relations of kind of area law and constant law. People that haven't been in contact with the literature of higher form symmetries will say, well, but this was not a perimeter law. Well, in fact, it is a perimeter law when the loop is very thin, but you can increasing the size of the width of the loop, it goes to a constant law. So let me think about area law and constant law, how they are related through this entropic certainty relation. The idea is that you want to check the value of the order parameter and relative entropy order parameter for this orange ring. And you have the knowledge of these black rings in the outside part, complementary rings, that they have constant law. Supposedly they have constant law and they have little correlations. In that situation, you can actually compute the relative entropy in this set of many black loops, and it turns out to increase to saturation with the number of black loops in an exponential way. Increase to saturation in exponential way, it means that due to a certainty relation, the relative entropy of this orange loop is going to decrease exponentially in the number of black loops that you can accommodate there. And you can accommodate a number of black loops that is proportional to the area enclosed, because you don't want they to be very near to each other in such a way that they have correlations, right? If they are uncorrelated, you can compute everything, and then you get an area law for the orange ring, because you have you can put an area worth of black rings outside. So, well, I think I have finished my time. Let me just say, well, so some final remarks. One is that the importance of wide loops in this thing, and it's quite strange, but it happens that in the literature there is basically nothing about Wilson loops, smear Wilson loops, for example. It's very difficult to construct in a smear Wilson loop in proper way. So we are trying to do that now. Another thing is that this certainty relation seems to point to some instability between in the relation between ultraviolet to infrared. One would like to say, well, what happens when I dilatate a ring? How these entropic order parameters move? It seems that because of this idea, once you have a set to some specific behavior for one loop, it triggers the same type of behavior, the opposite behavior for the complementary ring, and you have a kind of feedback relation that maybe can be used to understand what happens along the dilatation of the renormalization group. Another thing would be to compute these order parameters in weak coupling in non-abelian theories or in holography, for example. And more theoretical question, how to generalize these things to other topological features of regions or other dimensions. Thank you.
Thanks so much, Horacio, for the great talk. Are there any questions?
I have a comment. I don't know if it's probably relevant, but when there is this Megdal-Markenko loop equation where there is a loop Laplacian, and you can do e to the minus t Laplacian applied to a Wilson loop, and that's a unnatural way to smear it. Surely that has might have any relation. But it's just adding little loops, and then you sum everything, and you get like a bigger loop. I think you can do that in the lattice or things like that.
That would be nice. We have seen something like that. It was in the Euclidean framework, and with kind of let's say heat equation, something like that.
Yes, yes.
Something like that.
Yes, so you can, in the lattice, you can do first in the lattice, smear the lattice by averaging and compute the Wilson loop in the smear lattice, but that's equivalent to compute this smear Wilson loop in the original lattice, I think. So you can either smear the loop or smear the lattice, but it's equivalent. But I'm not sure, I mean, it's natural, but I'm not sure if it has any relation with what you're doing.
No, we are just trying to understand how to write down first and smear Wilson loop that is gauge invariant, that is the difficult part, and then just compute it in the limit of small coupling to see how it goes. It's just if you know expectation values of these smear loops, and you can play a game with improving this meeting, then you can get lower bounds of these things or upper bounds.
So this method will be you take a Wilson loop and then you take a lot of Wilson loops nearby by doing small deformations and you average everything. So you smear the Wilson loop by averaging many Wilson loops which are nearby in some sense.
But you average in the exponent, or you average, because averaging the Wilson loop itself, it doesn't look like the right thing to do.
No, you do it minus T Laplace and apply to the Laplace and apply to a Wilson loop give you another Wilson loop where you have an extra little loop basically. And then you do that many, many times. And that means that you have a lot of Wilson loops and you average the expectation. So the new operators is the sum of all the Wilson loops basically, which are near to each other. Well, so they are all Wilson loops. You are not defining something different, but you average many of them.
Okay.
Wow.
All right. Are there any other questions for Horacio?
I had a question also, like in the operator case, you have this current algebra. That's the usual way to put the symmetry, and in the Weidmann functions are the word identities. But there is any relation of that with this? Like,
yeah, I don't know. This is kind of
because supposing being integrating A, I integrate B, the magnetic field, that's the flux of the current. So there is some relation between.
Yeah. Yeah, of course. In some situations you can yeah, in some situations you can actually produce this twist or whatever, or the magnetic flux, or by using a current, for example. For example, this twist here, you can produce it by exponentiating something that is integration J0, the current in this region, right? Just producing the group operation there. But if you have, for example, a finite group of symmetries, you don't have a current, but this is still there. So this is still there. You can prove it. Of course, it's difficult to construct. There are like theorems that show you how to construct one, but they involve this Tomita-Takesaki theory and the J operation, the reflection, etc. So there are good tools at the algebraic level to say that they are there. How to construct ones that you can compute something, for example, expectation value is more complicated in general. Of course, if you have a current, you can actually try to compute something. For example, this is exponential of the current, and then you can compute the expectation values of those things. But in general, it's more difficult, yeah, to make a contact with a usual field theory.
I have a question as well. So do you have, in your paper, on global symmetry paper, you had a beautiful connection. Well, you made an observation, which is in holography, the fact that in the bulk additivity fails might have to do with the existence of intertwiners. And over there, the thing that that's confusing is that, so yeah, can you say a few more words about this? For example, are you thinking of a global symmetry? Are you thinking of a gauge symmetry? What is this group? Is this the ZN? Is it the ZN of SUN?
If you mean the case of the holographic case, I think I very much forgotten all that. So I will not add to your present knowledge, but in the so there were some things that do not match with this, at least with the present, with what I have talked here. For example, the fact that if you have, for example, two balls that are intersecting each other, in holography, the algebra is also non-additive. Somehow it's non-additive. So you produce an algebra that is bigger than the one produced by the two balls, right? So there are problems beyond the ones that I described here in the holographic case, I guess.
I see. I see.
I think.
So you're saying that even if we assume there's a huge symmetry group that is responsible and with lots and lots of intertwiners,
right,
we still have some paradoxes to resolve when the regions are overlapping.
Yeah, for example, you can think the simple thing is to think in the generalized free fields. At the level of generalized free fields, you also have this problem that they do not satisfy additivity for topologically trivial regions.
That's right.
Right? If you have because what you get is the causal wedge. You don't get just adding the algebras of two balls. You get the causal wedge, and you don't get the entanglement wedge.
That's right.
Or you can say you say, well, okay, I will always retain the causal wedge only, but then every region basically violates duality, right? So there are problems beyond the one that I described here. It's somehow like the non-local sectors do not only take into account the topology, but also the geometry.
That's right. In the ball.
Yeah, for a ball in the ball, yeah.
Yeah. Thanks so much. All right. Are there any last questions for Horacio? If not, let's thank Horacio again for the wonderful talk, and thank you so much.
Thank you. Yeah,
Thank you.
good to see you.
Have a great day.
Bye-bye.
Bye.